I'm Akshaj. I'm in my third year. I'm part of PS Innovation Lab, and I'll be giving a talk on formal verification in cryptography. So let's start with a simple scenario because the title sounds very complicated. So let's say Alice wants to send a message to Bob, right? It's Alice is asking Bob if he wants to go Indira Nagar at 7 p.m. I don't know, some random message, right? There is an assumption that no one else can read this message which Alice is sending to Bob, right? Uh, so over here it looks very simple. This is a direct link between Alice and Bob, right? But in reality, it's not as simple, right? Because you'll have, the message will go to Alice's router and then it will jump across a bunch of servers and then it will finally reach Bob's server and Bob finally gets the message, right? So what this means is this entire network is can be controlled by someone malicious like Eve, right? So Eve has full control over the network. What Eve can do is basically read all of the messages, but also like modify the messages or even intercept the messages and or send her own messages to Bob. Because all Alice can see is that she is sending a message out onto the network channel, right? And all Bob can see is that he is receiving some message. So this is the scenario behind the dollar Yao model, right? What occurs is you have an attacker who has complete control over the network, but uh, give you're not really concerned about the cryptography here, so you can't like check for weak encryption and crack it, with like a bunch of 4090s, entire rack of like supercomputers. Like there's none of that, right? Eve just has like a laptop or something, but she has full control over the network. And yeah, so here you can see Eve just modifies one of the message, and Bob has basically no way of like figuring it out, right? So how do we ensure that Alice and Bob have like can communicate safely? You come up with a protocol. What's a protocol? It's some set of rules that govern how like two entities communicate, right? So here it's very simple. Alice just says hello, Bob says hello. Alice sends a message. Bob's like okay. She sends an acknowledgement, right? So this is obviously a very simple protocol, but like most real world protocols do look something like this, right? You have your handshake at the very start, where you establish that I am Alice, I am Bob, and then you send the message and you get acknowledgement, right? And then maybe for leaving the session also you have some message. But you'll notice here there's no encryption, right? You can still read all of the messages. So what do here? You come up with a cryptographic protocol. What this is any protocol which is made specifically for security goals. So confidentiality, right? You don't want anyone reading the messages, or authentication, right? Because you want to make sure that when I'm talking to someone, the other person is who they say they are, right? If Bob is talking to someone, he needs to be sure that it's actually Alice and not just Eve, right? So you'll see Alice sends over her public key, Bob sends over his public key, we'll get into public keys, and the message is encrypted, right? You can't read the messages. So how do you ensure that such a protocol is robust, right? Because if you face with someone like Eve, who has full control over your network, he can reorder messages, right? Your entire protocol can break very easily, right? It's very complex. So use something called formal verification. What is formal verification? It's the act of proving or disproving that some system does what it says it does, right? You apply formal verification to a specification, right? You don't apply it to your program itself. So before you start, implementing some protocol, you say, okay, I have this logic of how the protocol works. Let me write a specification for it, and then I give it to a formal verifier, and then it's gonna solve it, right? And it's used widely in technology, right? The talk is about cryptography, but it's actually used everywhere from hardware, distributed systems, compilers. So hardware, for example, right? When you're making a chip, right? Like Intel, AMD, Nvidia, all these companies, chips are very, very complex, right? Because you want to make them as optimized as possible, right? And basically, you don't want your optimizations to accidentally break the logic of the code. For example, two cores access the same part of the memory, right? You want to make sure that everything still works, right? It's consistent. So you can use formal verification for this. And another thing is for distributed systems. when you have a very complex task which you can't run on one machine, you distribute it across multiple machines, right? And you want to make sure all of these machines agree upon some state. You don't want half the machines to say x equals 2, half of them to say x equals 5, right? So you need some consensus, and we have consensus protocols for this. And these can get very complex. There are a lot of edge cases when you try to come up with a consensus protocol, like Raft or Paxos. So you can use, there's a tool called TLA Plus, which is also a formal verifier, and you can use that to check it. And compilers. So there's a compiler called CompCert, right? And this is a C compiler which is formally verified. So compilers will try to optimize your C code as much as possible, right? So if one of those optimizations breaks something, then that is a vulnerability. So CompCert has had very few vulnerabilities compared to other compilers because it has been formally verified, right? So yeah, getting back to cryptography, you can also formally verify cryptographic algorithms. So for example, you want to encrypt with some key and then you want to decrypt it. You have some encryption algorithm like say AES, right? You can use tools like ROC or Lean for this. These are more mathematical, right? Lean especially is heavily used in mathematics, and that's because a lot of cryptography is mathematics, right? If you are developing a protocol, then you don't always want to think of the mathematics of how cryptography actually happens, right? Because that is way too complicated, and you trust that some mathematician somewhere has actually gone made a proof of this in Lino Rock, and then you know you are sure that it does work. You don't want to deal with it. What you do want to deal with it is protocol errors. So, for example, man-in-the-middle attacks, where this example where Alice sends a message saying that she's Alice, but then Eve just forwards it to Bob, and then Bob's like, "Okay, it's Alice. I'll send my password," and then Eve can read it, right? There's something that's called a man-in-the-middle attack, and also replay attacks, where because Eve can control the network, she can just store a message which Alice sends, and then maybe 5 days later she sends the same message coming run again at 7 p.m. Right? And then it's not applicable anymore. Right? That's a replay attack. Right? You want to make sure each message is tied to one session. Right? And so when you want to prove, you want to formally verify against protocol errors. You want to make sure your protocol is robust. Considering encryption, digital signatures, all of that is perfectly fault proof. There are two approaches. One of them is the computational model, where you say you have an attacker who has, maybe a couple of 4090s, not like an insane amount of compute, but like some finite amount of compute. And they can actually modify values, and they can say, okay, probabilistically, I can find the password like within this time. It's a weak password, right? And for example, chosen ciphertext attacks. This is something like you modify the ciphertext without decrypting it, and it still changes the plain text, right? So, for example, in the message coming run at 7 p.m., I change the even though it's encrypted, Eve can modify it so that it says come at 9 p.m. or something, right? Or come in 5 days. So when you want to prove while considering the encryption also, it can be very complex, right? This is what cryptographers actually do, right? On like pen and paper. And it can be like very annoying for the programmer to make sure that he or she doesn't actually program bugs while implementing it, right? Because all of these model specifications have to be written somehow. If it's simpler to implement, then it's also probably safer, right? The programmer isn't going to make many bugs. But depending on the model, for simple models, you can still use the computational model because it is ultimately more realistic. So you have EasyCrypt and also CryptoVerif, which is an extension of ProVerif, which also considers cryptographic algorithms, right? But for simpler models, you go with a symbolic model. So this is where you have your Yao attacker, right? And no, you can't really break encryption. You say, given the key, I can decrypt, right? And I can also create my own keys, for example. I can do whatever with the network I want, but anything that is encrypted is encrypted. Anything that is signed, right? Cryptography is basically perfect. And this is quite simple to automate, right? Because all you have is a collection of facts, right? Alice sends some information across the network, Eve now has access to it. Bob sends some information, Eve has access to it. And now Eve can either, save it, send it later. It's like a computer can brute force code quite easily, and it's easier to implement. And some tools for this are Camera Improver and ProVerif, which we're going to be talking about today. So Camera Improver is actually a more modern version, right? And but the reason I went with ProVerif is the syntax is much simpler for our 2-hour talk. So we'll get into the syntax. But first, is the symbolic model even useful? Right? Because yes, I'm saying we don't look at cryptography at all, right? That seems way too abstracted. So yes, it is absolutely useful. So these are a few papers I found interesting, right? So the first one, the EMV standard. EMV stands for Europay, Mastercard, and Visa, right? This has to do with credit cards, the protocol of credit cards. And so they basically model the entire protocol in Camera Improver, and they basically like Camera Improver went through every possible scenario of like sending this message, sending, putting it in this order, whatever, and they figured out that if you have a Visa card, you can basically, I mean, it used to be possible that you could basically do transactions without having to enter the PIN at all, right? And get the PIN bypass for Visa, and there was also another bug they discovered, which is that any Mastercard credit card, you could make any reader think that it was actually Visa. And when you make a Mastercard card into a Visa card, you can also apply the same PIN bypass for Mastercard also. So that was a pretty major vulnerability which was found by using the symbolic model, right? And also, I may say that PQ3, this is a blog post from Apple about how they verified the new encryption protocol against post-quantum threats, and they verified it using Camera Improver again, right? And symbolic analysis of TLS. So TLS stands for Transport Layer Security, and this is basically what underpins the security of the entire internet, right? So it's good to have like some formal verification to make sure that there are no vulnerabilities happening here. So getting to ProVerif. What is ProVerif? As I said, ProVerif is a automatic protocol verifier, cryptographic protocol verifier, which works purely in the symbolic model. So this means you just have functions like encrypt of some message with some key, right? You don't care how the encryption happens, but the encryption is there. It has been proved by mathematicians. It works, right? And this was created by Bruno Blanchet, who works in HAL INRIA in France, right? And it's a very old piece of technology, like 2002, and it has been updated, I think, in 2018 is the latest version. No, 2023 or something is the latest version. And yeah, the syntax is very easy to pick up. So okay, so before we get into protocol, how do we do encryption? Easy way, simplest encryption is symmetric key encryption, right? So you have some message, and then you say you encrypt the message with a key, and then you get some ciphertext, right? You don't care how this encryption happens at all. And to decrypt, you use the same key with the ciphertext, and you're able to get the message back, right? That is symmetric encryption. So how do we build a protocol based on this? You assume that Alice and Bob initially have some key already, right? So Alice encrypts her message with a key and sends it to Bob. Bob says, okay, sure, welcome, and encrypts it with the same key. How do they both know that the key is this? They've had it, they probably met up like before and like discussed, okay, this is the key, I'm going to use this later, right? So it's not fully realistic, but it's a very good protocol to like get started with Camera Improver. ProVerif. So I'll just go to the code right now. Okay, so I'll go to the code right now. And yeah. Oh, by the way, any questions, feel free to ask, right? Because I don't mind this being interactive at all, right? So feel free. And yeah. So yeah. Yeah. So what I have is yeah. So yeah. Okay, so do you guys have any questions before we get into the actual programming part of ProVerif, about how protocols work, why we need formal verification? Feel free to ask. Yes, go on. Olivia. So yeah, yeah. The question was, what exactly is Galaviao? Galaviao basically means that you have an attacker who has full control over the network, right? So an attacker. So in the symbolic model, we have like abstracted above like how actually encryption and decryption and all the cryptographic algorithms work. We are purely concerned with protocol errors. So we say that the malicious attacker Eve can modify messages, can read messages, can apply cryptographic algorithms herself. If Eve has the message encrypted message and the key, she can decrypt it, right? She can reorder messages. Basically send messages in a weird order could sort of confuse Bob or Alice into sending classified information. That's a Galaviao attacker. Does that answer your question? Okay, awesome. Anyone else? Yes.
They're sending an encrypted message, and the website has like a public key that it sends back, right? The key is still public. Can't you steal that and like encrypt whatever they send?
So we will. That's a question about. We will get to that in a few slides. Anyone else? Folks, any.
Like when you said weak passwords, right? So when the decryption, or let's say not decryption, when you said that you break a password, how does that happen? Like let's say we keep a weak password of 1 to 9. When it is broken, like what is the process?
So this is more to do with the computational model, right? So the question was, if you have a weak password, how is it actually broken? So you'll have attacker. Basically, you'll have attacks with. Okay, so when you encrypt a message, right? You have your message space and your ciphertext space, right? And what you have is basically every message has one ciphertext and every ciphertext has one message, right? So what you can basically do is you can say for this message, it's more likely to be this set of ciphertext than something else, right? And you'll say, for these set of ciphertext, these keys are more likely to uh, be true, right? You can also have something like uh, you might be able to run the encryption algorithm yourself, right? So you'll say, I have that's basically a chosen plain text attack, right? So you can encrypt any message you want with your plain text, and you say after encryption, I am getting this ciphertext, and I can analyze that ciphertext and say, okay, because of the way for example, this pairing is done or something, right? You can say because of that, my key must start with A or something. Like actually brute force your uh, way into the key. Does that answer your question? But this is again like obviously you'll for brute force you'll need like GPUs and stuff, like unless it's like because you'll have like say like a billion possible keys still, right? It's but then compare a billion to like 2 power 128 or something, right? That's a massive cut down, but it's still a lot. So you'll need to actually run some algorithm for a couple of days, and then you'll be able to reverse engineer the key, right? But here we're not concerned about that at all. You assume cryptography is fully perfect. Like you're only concerned about protocol errors. Yes. Anyone else?
Any more question, guys? There are no teachers in this hall, so you can ask anything. I mean related to topic.
Okay. I will get to the program. So yeah, what I have, yeah, is it visible for people at the back? Awesome. So this is basically how ProVerif code looks, right? So technically it's not code, it's a specification because you're not running the code, you're feeding it into a ProVerif, right? ProVerif is a software and you're feeding this into it. So you have basically what you do, how to make new variables is called free, right? Oh, actually before this, uh, if you want to try this along yourself, then there's this website, right? So if you just search, uh, if you search for ProVerif, right? Yes. If you search for ProVerif, you'll find this, right? And then you can go into the ProVerif website and you have a link for an online demo, right? So you can go to this online demo and basically run any code you want, right? Which is very cool. Yeah, you have this, and I can open this link if you guys want to visit this. Yes. Just a second.
Yeah, so like in this process, right, are you trying to like prevent the attacker to get the key itself or the message coming to it?
The main, I mean, so ProVerif allows you to test for both. So in the following examples, I'll be mainly focusing on the message itself, but you can also easily say, does the attacker, is there any way for the attacker to figure out what the key is? Like it's very simple to set that up. But basically, if you know the key, you also know the message, right? That is also there. Does that answer your question? Yeah, and also if you guys want the code, then I have the code on my GitHub, which I'll open, right? So these are the programs I'll be looking at. Yes.
Different is ProVerif from the other symbolic models? Like, why do you have a workshop on ProVerif and not the other ones? How, like, why this?
Why ProVerif? I mean, the main reason for talking about ProVerif is it's extremely simple to like pick up. The syntax itself is very simple. So initially, I was looking at Cameron Prover, which is the other symbolic model verifier, right? And if you look at the syntax of that, it looks very, very mathematical. Right? It does not look like there's no English words there at all, right? You just have like a bunch of letters and then symbols, protocols.
Which of the protocol verifiers are actually used in the industry right now?
So actually both are used. So I looked at recent papers, and ProVerif had more research papers compared to Camera Improver. But I feel like in the future, Camera Improver is gonna be used more because it is more modern, right? But again, you can use both. A lot of the features in Camera Improver have actually been brought into ProVerif itself with the recent update. So you can use both.
Thank you.
Thank you. Any other questions? Sure, I will get into the code then. So this is how you make a variable in ProVerif, right? You say free, and then this is basically where communication is gonna happen, right? You say a free variable whose name is C. You can name this whatever, right? Uh, and this is of type channel. This is where Alice and Bob are gonna communicate through. So Alice is gonna put a message onto the channel, and Bob is gonna receive some message out of the channel. You know what happens in that channel? You can put messages into it. You can take messages out, right? And yeah, we have types. So what are types? Are they like string, integer? No, they're not, right? So types can be basically anything you want, right? We are sort of abstracting above like actual data types, right? You can name a type like whatever, right? You can name a type with your own name, for example, if you want, right? It's basically why we need types is for functions. So for example, I have a type key, right? I'm gonna say for symmetric encryption, I have a function symmetric encrypt, right? senc, which takes in some big string with some string, right? Some sequence of bytes. And this is a built-in data type, big string. You take some message and some key, and then that results in some ciphertext, right? Uh, so yeah, you don't deal with how the encryption happens, of course, right? This is purely symbolic, right? And then you also have, this is called a destructor. So what a destructor does is basically given like two functions, it sort of says both of them cancel out and then you get back your original king. So here you have, you know, for any message or key, if you encrypt it, you encrypt your message using some key, and then you decrypt it with the same key, you get back your original message. Right, that's how symmetric encryption works. You encrypt it with some key, decrypt it with the same key, you get back your original message. Right. And I also have the secrets which I want to actually communicate. I have secret A, which Alice is gonna send to Bob, and I have secret B, which Bob is gonna send to Alice. Right. And these are both some strings, and they're also private. What does private mean? It basically means Eve does not have access to this, right? So this has not been sent on the channel before, right? Alice has already talked of some message she wants to send to Bob. Bob has some message he wants to send to Alice, right? Uh, Technically, you can use both of these secrets for either Alice or Bob, but we don't want to do that. For verifying a protocol, we say we only use secret A within Alice's score, and we only use secret B within Bob's score. We'll get to that. And we also have a key, which we say, okay, we have decided on before, right? It's private. And it's also a type key, because you want to be able to encrypt with it, right? For this encryption, we need a type key, and we have this key k variable. This is how we actually check what we want to prove, right? So here, this is the simplest syntax. We say query attacker of secret A. What this means is uh, you're checking if the attacker actually knows secret A. If there's any way for the attacker to figure out, through some weird protocol logic, what secret A actually is. And I'm doing the same for secret B, right? Can the attacker figure out secret A or secret B? And so these are processes. I'll start with this. Right. This is your main process. Right. So uh what you do here is basically exclamation mark stands for the macro, right? You are starting A of K indefinitely, right? Multiple times you start A of K and multiple times you start B of K, right? Because these because you also want to consider replay attacks. If A and B have one session, then later Eve might be able to exploit it. So Cameron runs indefinite w- sessions of A communicating and B communicating, and then mathematically figures out if there's any possibility of a vulnerability. Right. So what is A of K? We say let here for the process, and we say A, the function A, sorry, process A takes in some key, right? Because Alice already knows a key. So this is how I'm passing in the key to Alice. And then I use out. What out does is basically sends a message onto the channel, right? And the channel we define over here, right? And I'm using the same channel. I'm sending uh my message secret A symmetrically encrypted with my key K, right? And what happens next is we have Bob. What Bob sees is he gets some input. He's waiting for some input across the channel, right? Because he cannot see the network. All he sees is some uh, interface where he gets messages, where he receives, where he can input messages. So he's waiting for some input from the channel itself, which is of type big string, because once you encrypt, you get big string, right? And you say, okay, I'm getting this encrypted version of A and K, and then I just say the secret I receive is symmetrically decrypted X and K, right? Here you don't want to deal with how you actually just like, you don't deal with all of this logic. This logic is done. You just call it normally. symmetric decrypt of your ciphertext and your key K. And then once I have a secret, I want Bob also to send a message back to Alice. So I say send a message out across the channel, right? I want to symmetrically encrypt my secret with key K, right? And then, oh, while all of this is happening, Alice is waiting over here for some input. And now when Bob sends this message, Alice gets the same big string, like some big string, which in this perfect scenario happens to be this, and we can decrypt it using K, and then we basically get some output. So how do you run this? You can use the website itself. I'll show the website once, right? So I can just paste the code over here, and I can click on verify. So this just gives me that both queries are true. So what this means is, if you just look at the verification summary all the way at the bottom, it says not attacker of secret cafe. Basically, the attacker has no way of figuring out the secret, right? Because it's like perfectly encrypted, right? You have the same key, and then basically Eve has no way of figuring out what the key is. It's never sent over the network. You can also click here, HTML output, and then you can, if you have an attack, actually I'll show that later when you have an attack. So yeah. Any questions so far? Biggest syntax. Check. Feel free to ask if you have any doubts.
Mike is here.
Okay, no questions? Okay, cool. We'll move on then. So that was symmetric encryption. What we have next is asymmetric encryption. So what is asymmetric encryption? Basically, the problem with symmetric key encryption is you need to make sure, okay, Alice and Bob have met before, and they have to have a shared key, and also if this key is like 1 year old, then probably someone has already leaked it, right? Eve probably has it. You can't know for sure. So you have asymmetric encryption. Basically here you have two keys, right? You use a public key for encryption and a private key for decryption. So that means I have my secret key, S key, and I can derive a public key from my private key, right? I say secret key because I don't want to name both of them P key, right? So I have secret key and public key, right? And uh, what I reveal is my public key. So if I'm Alice, I can give Bob my public key. Bob can encrypt any message he wants with the public key, but he can't decrypt any message. No one can decrypt it with just my public key. I can decrypt the message because I have my secret key, right? So if you look here, pizza for example is encrypted with my public key, and it's basically encrypted. It's random, and you also have the asymmetric decrypt function, which takes in the ciphertext and the secret key and then decrypts it, right? So basically we have three new functions here. You have pub of S key, which takes in a secret key and then makes a public key. You have asymmetric encryption, which takes in a message and a public key and gives you some ciphertext. You also have asymmetric decryption, which takes in some message and some and a secret key and then decrypts it, assuming the secret key private public key pair is valid, right? You can't use any random secret key. So let's use this for a protocol again. We'll assume that both Alice and Bob know each other's public key initially, right? Maybe they've met up before, they've shared it already, right? So by somehow Alice knows Bob's public key and Bob knows Alice's public key. So the bottom of here is what information each person has. Like Alice has the public key PKA, the private key SKA, like secret key, and she also has Bob's public key. Like these are the three pieces of information Alice has, and Bob has these three pieces of information: his own public and private key, and also A's public key. So what I can do is Alice sends a message with secret key encrypted with Bob's public key. Right, secret key is the message Alice wants to send. She encrypts it with Bob's public key. Now Bob can read this message and can decrypt it with his own secret key. Bob sends over the message using Alice's public key, and Alice can decrypt it with Alice's private key. Does that make sense? Yes.
Slide. So Alice and Bob's are generating two pair of keys,
Yes.
private and public,
Yes.
private and public.
Yes.
So Alice is sending want to send something, but with encrypted form.
Yes.
Okay. So to do that, Alice is using Bob's
Public key.
public key,
Yes.
and then he will decrypt it with his own private key.
Yes.
Right. So what is the platform or what is the source where he's creating both pair of key?
So that's a very good question. So you have algorithms like RSA where you can generate a pair of public and private keys. But so what we assume over here is these algorithms already exist, right? So there are algorithms like RSA, LGAML, right? There are some cryptographic algorithms which mathematicians and cryptographers have proved is secure, and you basically aren't concerned with them, right? You say, okay, I know these exist. I know that Eve cannot break it without the private key. Is there any other way she can break it? Right. That's the entire reason we're doing a symbolic model. Because if we obviously this is a very simple back and forth protocol. But if you have a complex protocol which granting statements and some other like conditions, edge cases, then dealing with the exact cryptographic algorithms of how all of this stuff is actually happening mathematically becomes complicated, and the programmer doesn't really want to deal with all of this, right? So right now we're assuming this works, and yeah, guess I can answer your question.
Like as much I
Yeah.
know, well, you are creating a pair of key organize, then you will use the puttigen generate a pair of key.
Yeah.
Okay. So that is the concept of my question is like apart from that puttigen general want to generate a pair of key, then what you are using?
So basically, I'm not concerned with the tools right now because each tool is implementing some algorithm, right? So yeah, you have RSA. If you want to go post quantum, then you have various uh, various other algorithms, right? So there are a variety of algorithms, but each algorithm has some way of deriving a public and private key. And encryption is done using the public key, decryption is done using the private key. So the beauty of this is even like 40 years in the future when we have quantum computers, when all our current encryption tech is like broken, we will still have some public and private key using some different algorithm, right? So and any protocol others which work now will also work the same later, even though your encryption algorithms themselves are like much more advanced. You don't care about them. There's some public key and some private key.
So what will be the medium through which that key is getting exchanged?
Sorry, can you repeat?
What will be the medium? What will be the medium where Alice is sending
Thinking the
Bob?
public key to Bob and Bob.
Yeah, yeah. What?
That's a good question. We will get to that in a few slides.
Thank you.
But right now we assume that Bob already knows Alice's public key and Alice already knows Bob's public key. That is a naive assumption, I agree. But we will get into why it's actually more complicated. Any other questions? Yes, sir. Yes, sir. So the encryption and decryption.
Yeah, just to answer your question, the key generation is basically done by a high-level mathematics. Okay, it's a modulo arithmetic which is at a very high dimension. So the number of possibilities of pairs of public and private keys are very high. And it is very difficult to guess, and it can be changed by a process as to whether it is effective only for 124 hours or one session. So the secrecy is maintained for that. And how is it exchanged with the users is using Diffie-Hellman exchange algorithm. So that's a very proven and established algorithm by which the key is exchanged. So your question is, how is it generated? What is the tool you're using it for? So that is based on a mathematical function which generates that. So it is more than 256 bit and 1024 bits and so on. So there are standard methods to generate the keys for. Like in the typical case of banking applications like a net banking. So ICICI Bank is one and users are so many. Okay, so they can't have individual pairs of keys with ICs. So that is where the PKI comes into picture. And
Thank you, sir. Any other questions about how asymmetric encryption works? Cool. I will move on to the code then, right? So yeah, we have a channel here again, right? Where Alice puts in messages and Bob's reads messages or vice versa, right? And I have two new types here. So before I just had one key. Now I have a private key and a public key. And given some private key, I have a pub function which can basically create a public key pair, right? So given a private key, I can make its corresponding public key. And for asymmetric encryption, I have a function which takes in a function asymmetric encryption, which takes in some big string, takes in a public key, and then returns some other big string. So this will be a message and this will be a ciphertext. Why am I calling it message and not, why am I calling it big string and not message or ciphertext? Because big string is built in, you can use message and ciphertext, right? The types mainly matter for, uh, basically when you're doing functions and stuff. So here big string works for me. So, and also you can encrypt the same message twice, right? So Gary doesn't make sense to use message and ciphertext. So just going with big string for now. And then my destructor function with this decryption, if I have some message m, some message k, some private key k, sorry, then I can encrypt it using the public key associated with that private key, right? And once I have this, I can also decrypt it with the original private key and get back my original message, right? That is asymmetric encryption. That's how it works. So I hope this makes sense. It looks a little bit messy, but then once you understand it, it's fairly straightforward, right? So I also have my secrets, right? Secret A and secret B, which are private because Eve doesn't know the secrets. Only Alice and Bob know the secrets. Alice knows secret A, Bob knows secret B, and I'm checking if my attacker can figure out what secret A is or figure out what secret B is, right? So let's look at my main process. I am generating a new private key, SKA, secret key A for A. And I'm also saying let my public key, PKA, be pub of SKA. Right, I'm deriving the public key and just storing it in a variable. Right. I'm gonna say in over here. This is not the same as the channel in. This is a bit confusing. I agree. But basically, this is like an if statement. So what we do is let some new variable equals the result of some function, and you say in, and then if the type of this function matches, we can also assign type over here, right? You can say big string, right? So you say if this is possible, if because you can also, we'll see in the future why this may not be possible. If the type of SK matches the type of pub, and you can assign it, then you move forward to the next line after in, right? That's what in means. It's like an if else basically, and that's why I don't have a semicolon over here, right? And I can do the same thing over here, right? I have a secret key for B. I'm going to also derive the public key for B. And into A, I pass in B's public key and A's own secret key. Right. So I'm assuming A already has B's public key and B already has A's public key. And they have their own secret keys. So let's see what we actually do with them. I am sending a message into the channel, right? Out of C, I'm putting a message onto my channel. I am asymmetrically encrypting my secret with B's public key, right? And I am waiting for an input. Meanwhile, B gets the input from A, right? B gets this encrypting, and then B says, okay, I will decrypt this with my own secret key, right? And then, so for example, over here, if this public key and this private key don't match, then the encrypting would fail, and then because of the in, it will move on to the next statement, right? It's a tiny bit confusing the syntax, but yeah, that's basically why we have in. After any let, usually you'll have in. And once I'm able to decrypt A's secret message, I also pass my own secret B, encrypted using A's public key, and I am able to receive it over here and then decrypt it. So this time let me run it over here itself. So ignore this for now. I will run. If you have ProVerif installed, you can just run ProVerif and your PV file if you're not using the website. Wait, let me zoom in. Right. So I can run. If you zoom fine, can people at the back see it? Awesome. So yeah, I can run ProVerif followed by some PV file, and I get a lot of code, right? So all of this is there in the HTML output if you want to explore. We will see that in the next example. So because next example will be much more interesting. So what it does is basically numbers each instruction, right? So I have a new secret key. I'm gonna making my public key. I'm gonna new secret key. I'm gonna make my public key. And then this is basically my A process, and this is my B process. I'm basically assigning a number for each of them, so I can point out during this step this happening. And at the very end, I see both my secrets are safe. The attacker has no way of figuring out my secrets, right? So, any questions so far before we move on? Yes.
Been checking there if the query attacker, like the attacker has the public key or the private key.
Correct.
How does that happen in real time? Like,
How does the sorry? Could you repeat your question?
how does like we do send messages and receive messages right now, but then how do we know the messages are safe or not? Like the attacker hasn't gone through our message.
Correct. That's why.
Like
So,
here you checked it.
so your question is basically, in this simulation, we can see that the attacker can't know the secret, but in a real scenario, how do we actually know it?
Yeah, yeah.
So again, so the reason we do all of this is we make before we actually program a protocol, we model the specification for it, right? So if you know, so what I'm writing in ProVerif, it's not actually running anything, right? There's no network traffic happening between two desktops, right? It's just a simulation. And basically, before I develop a protocol, I will check it using tools like this, ProVerif for camera improver, or even computational models if it's like possible, feasible, right? And I go through all of this, I make sure that okay, it looks safe, and then I start actually implementing it. So once I have it implemented, I already know that it's safe by that point. Does that make sense? No, so before you even program your protocol, so when you send a message, your protocol already exists. And it has already been proven by these formal verifiers. So WhatsApp, for example, uses end-to-end encryption and stuff, right? All of those, all of that protocol and the algorithms have been proven separately, right? You have lean proofs for your cryptographic algorithms, and you have, you know, tools like this to prove how the end-to-end encryption protocol actually works, right? Between WhatsApp servers and you and your friend, right? All of that has been proven, and then it has been actually implemented into WhatsApp, right? Does that answer your question? Awesome.
So ProVerif here has only been used to verify these protocols, right?
Yes.
What about verifying the very implementations of these algorithms such as RSA or LGML. So let's say you have libraries in Python. So is there any way to verify those libraries itself?
So the point of a okay. So first of all, you said RSA and stuff, right? That's not a protocol. That's an algorithm, right? That's an encryption algorithm. And you can use tools like Rock and Lean to verify that those algorithms work. Now you have your algorithms and then you implement them into Python and release them as libraries, which anyone can use. To make sure that those libraries are safe, use different forms of testing. You use, for example, fuzz testing, where you generate random input. Let a computer generate random input, give it to it, and then you see how your actual Python program behaves, and you try to catch errors that way.
No, what about these libraries? So here, the type of verification that I'm talking about is whether these implementations accurately implement the algorithms itself. So
Correct.
are those kind of verifications even possible in ProVerif?
No. So your question is about whether you can test the actual implementations themselves of the algorithm.
And verify if they are actually
If they actually hold
properly
up to the
verified.
implementation, or there's some implementation error, you mess up how you assign your variables or something. You assign a large variable, you insert you sorry you say a long variable is actually an integer or something, like some error while actually implementing, like not considering the algorithm.
No, not a technical implementation as
Okay.
per se. We're basically checking the equivalence of the mathematically in an equivalent way as a library.
Correct.
So we're basically verifying these two things and we're checking whether they're equivalent in a sense.
Yeah. For that, you'll usually have to do some sort of test, unit testing. Like you have test cases. You say for this input, I should get this output, and that is obviously you can't write everything by hand. So you let a computer generate a bunch of random test cases. You say mathematically it should be this, but according to this algorithm, how does it actually do? I think there are a few public test cases, test case datasets for famous algorithms. So that is usually used. I actually saw an interesting paper about how for I think ProVerif was used to model the specification, and then based on the specification generate a bunch of random test cases which could then be used for the implementation. Right, does that make sense? So you use your ProVerif and you modify. It's not native ProVerif, it's a version of ProVerif that they created, and they generated a bunch of random values which conform to the ProVerif specification that they wrote of how the protocol should behave, and then they actually tested it against the Python program or whatever of the actual implementation. And they found a few vulnerabilities also this way, I think. It's a very cool research paper. So probably afterwards I can probably share the paper with you.
Sure.
Yeah. Yeah. Any other questions? Yeah. Go on.
So when you're using the query attacker, so you said you're checking if the attacker has access to the key or whatever. So
Correct.
what exactly are you checking for? Are you checking for MITM attacks, or what exactly is it doing that it's verifying?
So right now we don't care about the attack. We assume ProVerif is gonna handle all of those attacks, and we'll say using any attack possible. Is there any way Eve can figure out what the message is? So MITM attacks we will get into in the next example, right? So yeah.
I just wanted to know what exactly it is doing that it's finding out. So are we not concerned with that in this?
So what it's doing is basically, so how ProVerif actually works is it mathematically models all of this as logical statements. Right? You say at this state, A has this information, B has this information, and Eve, who's observing the channel, has all of this information. So from there, maybe Eve can and Eve can maybe use a function which was some key which was saying much earlier. Right? It basically tries out every possible case. Right? It traverses the entire state space and then figures out is there any a series of operations that Eve can do to figure out the message. So I would say the next example should probably clear the doubts. So after that, if you still have a doubt, can. Thank you. Okay, I will move on to the next example. So what we assumed over here is public keys are already shared between them, right? We assumed Alice has Bob's public key and Bob has Alice's public key. Obviously, this is not actually shared like this, right? You need to somehow put it out there. So here we are sharing public keys over a network, right? So we say somehow Bob's public key is on the network. Who has shared it there? I don't know. Maybe Bob himself has shared it. Maybe through some third party it has been shared. For example, right? Somehow Bob's public key is on the network, and Eve has access to it, right? And so now Alice knows Bob's public key, right? And Alice sends out her own secret encrypted with the public key, and also sends her own public key, right? Because Bob doesn't know Alice's public key at this point. So Alice encrypts it with Bob's public key and also sends her own public key saying, if you want to talk to me, encrypt it using this key. And Bob's like, okay. Bob uses his own secret and his public key and then sends it back, right? So yeah, they just know their own public and private keys over here. And yeah, does that make sense? Right, so we will move on to the code if that's fine. So I have my channel, right? I have public and private keys. And I'm saying I make a public key from my private key, right? I'm gonna have my asymmetric encryption. You know, I can asymmetrically encrypt using my public key and decrypt. Once I've encrypted with my public key, I can decrypt with my private key and get my message. The main difference over here is with AMB. So I guess we'll look here first, right? So I'm making my private key for A and then also deriving the public key. I'm making my private key for B, deriving the public key, and then I'm saying immediately after doing this, I'm outputting my public key onto the channel, right? So I'm using the channel itself here in my main process. I'm saying PKB should be out on the channel. And then after PKB is on the channel, it's available for anyone to pick up a news, including Eve. I say, okay, A, you can now have your own secret key and private key. So the reason I'm passing him private key of A over here is mainly because it's convenient, because I already calculated it over here. I don't want to calculate it again over here, so I'm just passing it here. You can just pass secret key and then calculate the public key later. And also for B, I am passing the secret key, right? So let's look at what A and B are actually doing. A is going to take in the public key from the channel, right? So A is going to see on the channel is there any data which is of type public key, and she sees this and says, okay, this is Bob's public key. I'm going to encrypt my message using Bob's public key, and I'm also going to send out my own public key so that Bob can communicate back to me, right? Because Bob can't encrypt otherwise. Bob needs Alice's public key, and this is where it's being sent. And then Alice waits for Bob's response. Bob takes in this input, and Bob says, okay, I have my encrypted secret A, right? Which is also of type big string. And I also have PKA, which is a public key. So I can use this for encryption now, right? And I'm saying this entire thing I derive from whatever I got from the channel. And then I say, okay, I have my response, and I'm decrypting it using my own secret key. So if, for example, if Eve sends something encrypted using some other her own public key or something, over here the step would just fail, right? And ProVerif stops searching, because if the protocol fails, they'll probably just start it again, right? There'll be some error. And after that, I send out. So Bob now has Alice's secret, and Bob sends out his own secret encrypted using PK, which we just got here, right, from Alice. Now Alice reads that, and then Alice can decrypt Bob's message using uh, her own secret key, right? So this protocol looks simple, right? So I'm just sharing public key over the network, but this is actually very interesting, because if I were to run this, like ProVerif second program. It actually fails. So Eve has a way of getting both Alice's secret and Bob's secret over here. And this is very interesting because it gives you a very clean output. So I will actually show this on the website itself, right? So copy this. Right, I paste the entire program over here, and yeah, I get the same output. Both queries have failed. So I can look at the output, and I see a lot more stuff. Right, the what I really want to focus on is verification summary, which we saw, and also explain derivation, which I think makes the most sense. So we look for how Eve figures out Alice's secret. Right. So this is the output. The attacker has some term K. So what this means is Eve is basically creating her own private key right now. And Eve uses the pub function to make her own public key. So now I have PKE and SKE, right, which are Eve's public and private keys. Right. And the attacker has public key which may be received at input 8. What is input 8? Let's just see. It is this Alice's process, right? So Alice is taking in a public key from the network. But now, because Eve put her public key out on the network, Alice is actually taking in Eve's public key, right? So this is a classic man-in-the-middle attack, right? So Eve is now intercepting whatever message Bob put out with his public key, and Alice now has Eve's public key. But Alice doesn't know this. She still thinks that she has Bob's public key when it's actually Alice's. So after this, all of this goes on, right? So after this message, like the encrypted message, is sent to the attacker with the secret and the public key pub of K. So this is what the attacker currently knows. The attacker now has asymmetric encrypt of Alice's key with pub of K, which is Eve's public key, and Eve also has her own public key. And after this, Eve has Alice's public key because Alice thinks both, right? And this function basically says given two elements, Eve can basically subtract those into two single elements, right? It is very obvious to us, but for ProVerif, this is an additional step. And now Eve has a secret encrypted using pub of K, which is her own public key, and she can just use decrypt because she also has her own key, and she gets a secret, right? So to give a more visual demonstration of what's happening, yeah. So Bob is basically not involved in the communication at all, right? It's only Alice and Eve communicating, but Alice has no idea. Alice thinks she's communicating with Bob, but it's actually Eve. So this is the example for how Eve gets Alice's secret. We can also see how she gets Bob's secret, right? We can go over here for Bob's secret, and so you can basically she makes her own secret keys again, like private key and public key. And I'm sending it like output 5. What is output 5? Yeah, she's putting it out on the network, right? And she's also taking in oh wait. Okay, so this is actually Bob putting his public key out on the network, right? So that's my bad. Bob puts his public key out on the network, and then Eve is able to get Bob's public key. And now Eve basically creates her own secret. So Eve doesn't have anything to say, but she just says, okay, I'm sharing a secret, and I'm also encrypting it using Bob's public key and sending it to Bob, right? And now Bob thinks, okay, Alice has sent me a message and also Alice's public key. I can respond by encrypting using Alice's public key. But Bob doesn't have Alice's public key at that point. It's only Eve's public key. So I can show you visual for this again. Yeah. So Alice is basically she gets Bob's public key and she tries to send this, but then Eve basically doesn't care. The message goes nowhere, right? But Eve gets B's public key. B says, okay, I'm actually sending some random noise. I'm saying it's secret A, and I'm also sending my own public key. And now Bob, he doesn't have any idea that this is happening. He thinks he's talking to Alice. He encrypts his secret using Eve's public key, sends it to Eve, and I know Eve has obviously her own private key. She can decrypt this and get Bob's secret, right? So this is an example of a man-in-the-middle attack, right? So basically, we need to somehow fix this protocol to make sure that Alice knows that she's talking to Bob and Bob knows that she's talking to Alice. So, any questions with this part before we move on?
When you say that like public key is derived from a private key, does that mean that the reverse can also work? Which means like if you know a public key, you can derive the private key of the person too, right?
That is a very good question, and the answer is no. Because of how these cryptographic algorithms are generated, you can get a public key from a private key. But given a public key, you cannot find the private key unless you go to every possible key and see where it maps, and then this brute force the private key. There's no way of doing this. So that's actually a very good question. I should have mentioned that. You can always go from private key to public key, but you cannot take a public key and derive the private key back. Like you'll notice that's why there's no function over here for going back. Right? It's a one-way operation. You can go from secret to private, but not back. So yeah, does that answer your question? Awesome. Anything else? Awesome. So yeah, this is Alice and Bob's attacks. So how do we solve this? We'll need to somehow be able to authenticate that what Alice sent is actually from Alice and what Bob sends is actually from Bob. So we have another cryptographic algorithm called signatures. So again, we have this part which looks similar, right? We have a sign secret key and a sign public key, and you have your sign public. I just put S at the start of everything because it's basically the same thing, right? You have a pair of public and private keys for signing. So what can you do with signing? You can take a message and you can sign for a given message with a secret key. So for signing, you use the private key, right? And you don't share this with anyone, and you get back this, where the message itself hasn't changed. You can still see that the message says pizza. So I can just run the get message function and get back the string pizza. Or I can do check sign with Alice's public key and verify that the message is actually from Alice. So you can sign using a private key. You cannot sign using a public key, but you can verify that it has been signed using a private key, right? So if I have a public and private key pair, I will sign it using my own private key and give it to you, and give you my public key and say you can check it against this public key. It has actually been signed by me. So this message is actually from me, right? So how can we use this? So this is a slightly more complex algorithm, right? So again, we assume that Alice gets Bob's public key from somewhere, right? Either Bob sings or someone sings, but Eve knows the public key, Alice knows the public key, it's public, right? And let's try to unpack this, right? I have Alice's public key and NA. What NA is some random number, right? It's called a nonce. A nonce is some number which you use only once. So so today I am using this conversation. Tomorrow, if I want to have another conversation between Alice and Bob, NA will be fully different, right? We'll see where NA is used. I am encrypting this tuple, these two values, with Bob's public key, which I've just received. And I'm also signing it with my own secret key, right? So this part looks sort of similar to the last time, except I'm also signing it with my own secret key. So now Bob can read this, and then Bob can see, okay, I have this entire encrypted message, and I say it's actually from Alice. I am sure of this because it has been signed, and I can decrypt this using my private key. Like no one else can decrypt this because anyone can see this, right? So signing doesn't actually change your message. You can still read whatever is signed, right? And basically, but only Bob can decrypt this and get PKA and NA. So Bob sends back to Alice, NA encrypted using Alice's public key, right? Which he got from right here. And he's basically saying, look, I decrypted this. That means it's actually me. And he also signs it using his own signing key, right? And now that the both know what NA is, and Eve doesn't know what NA is, this is essentially the same as the first protocol we saw, where Alice has some key, Bob has some key, both of them know the key, Eve doesn't know the key. So here you can just use symmetric encryption. You don't need asymmetric encryption here at all. Why do we want this? Because asymmetric encryption, algorithmically, if you actually see, it's more complex, uses more power, takes more time. You don't want to asymmetrically encrypt every single message. You can just use symmetric. So I'm just sending my message encrypted with NA. I'm sending Bob is sending his secret encrypted with NA, right? So let's see how this actually works in ProVerif, right? This reprogram. So yeah, I have my symmetric key, S key, and my symmetric key function which we saw earlier. Given some message and my symmetric key, I can make my message again, and I can, if I encrypt using my key and then decrypt using the same key, I get back my message, right? And this basically is used for changing the type. This is used internally by ProVerif. This doesn't actually affect the logic that much. Basically saying, given some key, because I want to send keys, encrypt keys, my encryption function takes in a big string. So I can convert my key into a big string and then encrypt it. Basically, it's what it's saying. That's what a type converter means over here, right? So this doesn't actually matter with the protocol itself. You can actually make ProVerif ignore all types if you want to. It's usually not recommended, but you can. And you have your asymmetric encryption, public and private keys. You can derive your public key. Oh, it is okay. That's a mistake. Yeah, you can derive your public key, and you can also encrypt and decrypt, right? You can encrypt using your own public key, and you can decrypt using the private key. And here we have signatures, which is the new part, right? We have SPK, which is my signing public key, and I have SSK, which is my signing private key, right? Secret key. So given my secret key, I can run spub and get the corresponding public key. I can sign any message using my secret key, not the public key, using the secret key and then get back some other message. And you also have two descriptors where you have get message from some sign x comma y and you get back x, right? X is some big string, y is some SS key. And then if you sign it, you can basically remove the sign and get back your original message. You can also check a sign using the public version of the private key, right? So y is some private key. You are checking this some sign message against the public key and you get back x, right? And of course I have my secrets, I have my query attacker, and over here this looks new. So this is actually the same, right? I have A's public and private keys. I'm gonna have B's public and private keys. I'm gonna put B's public key onto the channel, and I also have sign public and private keys for A, like SSKA and SPKA, right? And I also have the same for B, right? This is used for signing. This is used for verification. So for A, second the secret key used for encryption, the secret key used for signing, and also B's public key used for signing, right? I am not sharing B's public key for encryption. I'm sending for signing, and for B also it's the same. His own encryption private key, his own signing private key, and also A's public key for for signing, right? So let's look at the code. For A, I am sending in no, A takes in B's public key, right? And I create some new nonce which is of type S key, right? I'm generating a new key which I want to use later for symmetric encryption. And I'm basically saying, okay, I want to make a big string version of this because I want to encrypt it. I say S key to a big string of NA, right? And what I'm sending is this. I'm sending my public key and my random nonce. I am encrypting it using B's public key, so only B can decrypt it and get this nonce. And I'm also signing it with my own signing key, right? So when B, and then Alice waits for the message. So now B gets this message, B's text is sign. B's is actually from okay, this would be A. That's a mistake. Yeah. B checks that X1 is actually from A, right? And Bob says, okay, it seems to actually, if it's not, Klianka program failed, right? So ProVerif doesn't even consider it will be like some protocol went wrong and Alice and Bob have to restart the protocol, right? So assuming this works, it's actually signed by Alice. Bob knows, okay, this is actually Alice's public key, it's not Eve's public key. And then I'm also sending back NX, which is what I received. Like NX is basically NA, but then I don't know if it's from Alice or Eve. I mean, I know it's from Alice, but I say NX, right? And I'm decrypting this and getting those. And I'm also sending NX encrypted using Alice's public key, so only Alice knows what NX is, which is NA again. But I'm also signing it with my own private key, right? Signing private key. And now that Alice gets this, Alice also checks this against Bob's public key. Alice sees, okay, it actually seems legit. And now that both of, and she also takes this NABS by decrypting, right? She's verifying that this is actually equal to whatever you get by decrypting. So now now both Alice and Bob have a common key which is NA, right? And now it's just straightforward, you know, okay, actually use asymmetric encrypt. Okay, I can just use S encrypt. Okay, the program is slightly wrong. I should be using symmetric encrypt over here, right? I mean, this also works because I know the public keys are also verified. But yeah, I can just use symmetric encrypt with NA, and then I can symmetric decrypt with NA again. And here I can do the same thing. Symmetric decrypt with NA. And yeah, here I am decrypting using NA. Okay, I forgot to change that. My bad. Okay. Yeah, now I have the secret. I encrypt it, share it, and B gets it, and then does the same thing, right? So is this possible to figure out? Let's see. ProVerif. Okay, there's a small error somewhere. Line 58. Oh, this will be SP. I changed this right now. Yeah. I'm checking against Alice's public key, not her private key, which only Alice knows to sign. And Alice's public key is revealed. I'm going to check against the public key. So I hope this works now. Okay. Get a few problems. Alright, for Bob, I need to use NX. And that should be fine, I hope. Yeah, awesome. And we see that, yeah, it actually works. Because we authenticated the protocol, Eve cannot actually figure out the secret between Alice and Bob. So, yeah, if Eve tries to do something like she did before, she'll say, actually, Bob's public key is PKE. And Alice signs it, and then sends it over, and then, signs it with E. Because, P's public key is basically out on the channel. Eve can change it to her own. And then when Alice sends this, Eve can check that it's Alice's signature. But then when she sends this over, you will notice that she can't actually figure out. Alice can figure out that it has not been signed using Bob, right? Because this will be, this will be signed using Eve's private key. So Eve cannot forge Bob's signature, and Alice will know, okay, this protocol has gone wrong. Eve is smuggling with something. I'll just talk to Bob later. So that's basically. Any questions so far, by the way? I'm assuming there's no questions. Awesome. So that's basically the conclusion of the talk. So basically, as a summary, we saw how ProVerif can be used to verify protocols. Right? It's a symbolic model, $Yao model, where you're not really concerned about how the encryption can be cracked, but you don't know that messages can be interleaved, messages can be forged, whatever. Right? And given some specification, ProVerif will give you the entire trace of like how Eve can actually break into the protocol and figure out all of the stuff. Right. So yeah, thank you.